Each pseudo-random number xn is generated by multiplying the previous number xn-1 by m. The number xn-1 can have as many bits as p, so if p has b bits, xn-1 can also have b bits. Since m must have at least b over 2 bits, the product mxn-1 can have 3b over 2 bits. If the register size is 63 bits, then b can be at most 2/3 of 63, namely 42, which means m could have at most 21 bits. It is better to make m larger than the square root of p. A reasonable trade-off is for m to be 25 bits and for p to be 38 bits. That lets the period be up to 2 to the power 38. The property that is required to make the generator unpredictable is that the generated units have equal or uniform frequencies, pairs of units have equal frequencies, triples and quadruples have equal frequencies, and so forth. As a practical matter, you need not go beyond octuples, or at most dectuples of bytes. If you want to be absolutely dead sure, take your desired key size and divide by the size of the generated units. For example, if your key size is 128 bits and the PRNG generates 4-bit hex digits, then you might require the n-tuples to have equal frequencies for all values of n up to 32. Anyone who does that is clearly obsessive-compulsive and should seek treatment. Even for 4-bit random numbers, it is neither necessary nor useful to go beyond 16 tuples, or at most 20 tuples, sextectuples or vigintuples, that is 64 or 80 bits. Emily would need more than 2 to the power 64 or 2 to the power 80 bytes, respectively, of known plaintext to exploit these uneven frequencies. Even if Sandra never changed her key, it is implausible that Emily could ever accumulate that much material. To put this in perspective, suppose there were a satellite that beamed down telemetry at the rate of 1 megabyte per second. Suppose further that it beams this data down using 2 different key streams simultaneously, and that Emily has the key for one of them. Even though she is getting plaintext/ciphertext pairs at the rate of 1 megabyte per second, it would still take about 585,000 years for her to collect 2 to the power 64 bytes. Even with 1,000 satellites all using the same keys, it would take 585 years. If the frequencies of the n-tuples are equal for every value of n, then your generator is true random. You have found a mathematical algorithm for generating true random numbers. Congratulations! Go collect your Fields Medal. In order to have the tuple frequencies equal up through n tuples, it is generally necessary for the generator to have seeds that are themselves at least n tuples. For multiplicative congruential generators, the single unit and pair frequencies are uniform, but the triples frequencies are never uniform, and the n-tuple frequencies for n greater than 3 are very far from uniform. Most of these frequencies are 0. Cracking a multiplicative congruential cipher is straightforward if you have a few characters of known plaintext, and if the cipher makes it easy to determine the random output from a plaintext/ciphertext pair. That is, if the combining function is XOR, add, or MAD. For example, if the cipher exclusive ORs the key byte to the plaintext byte to get the ciphertext byte, then all Emily needs to do is exclusive OR the plaintext byte with the ciphertext byte to get the key byte. If the generator has a 31-bit or 32-bit modulus, it is feasible for Emily to try all 2 to the power 31 or 2 to the power 32 values for the seed, even on a PC. The known plaintext characters would be used merely for verification. If the modulus is larger, say 48 or 64 bits, then the first 2 or 4 known plaintext characters are used to limit the search range. The first random output limits the current state of the generator to a narrow range, 1/256th of the total range. A second known plaintext character gives a second output that limits the state to 1/256th of that range, and so forth. Thus, a single multiplicative congruential generator is not cryptographically secure. It is possible to use a much larger modulus, using big integer multiplication techniques like Karat-Zuber or Toom-Cook, but that would sacrifice the high speed of this class of generator. There are faster ways to produce cryptographically secure generators, so this book will not cover big integer multiplication methods.